Hello everyone, welcome to YouTube channel Energy-Exergy-Theory-Applications. I am Professor Tatiana Morozyuk and I am the author of this YouTube channel. Today we are with the topic exergy. All lectures have a very dynamic style of presentation. Definitely some of you would like to learn more, particularly about exergy. We will be happy to answer your questions and provide with an extended information. Our contact email you can find in the description of each video. Please support our work with a like to this video, subscribe the channel and share the link with your colleagues. Lecture 5 on exergy analysis. We will continue with chemical exergy. Chemical exergy part 2. As we already discussed in the previous lecture, that a chemical exergy has different definitions. As exergy also has different definitions, not alternative, one supporting to other. And chemical exergy can be discussed as a departure of the system from the exergy reference environment when already system and environment have the same temperature T0 and the same pressure P0. And chemical exergy has two contributions. Therefore, we can discuss about concentration exergy and we can discuss about reaction exergy. Concentration exergy associated with work that can be produced when system is brought to the equilibrium with the environment when the same substance exists within the thermodynamic environment, and reaction exergy associated with the work that can be generated or supplied in order to generate substance that does not exist in the reference environment but exists in the real life. And we already discussed that chemical exergy always should be discussed regarding the state of the system. Is it gases, it is liquids, or it is solids? Because exergy reference environment is not homogeneous, it is divided into three parts. So let us start with gases, because with gases it is always easy to follow and we can always apply even ideal gas if we need to discuss properties or mixtures. Okay, when we discuss about gases in chemical exergy of gases, we need refer to the atmosphere. And we know that atmosphere is not homogeneous. According to Chargot's model, we have quite a lot of pure substances, and also we have water and carbon dioxide as the description of the theoretical atmosphere. So we can, theoretical atmosphere from thermodynamic point of view, we can describe as, of course, one system, because all gases together, it is mixture of gases, and the entire atmosphere will be at the temperature of the environment and pressure of the environment, but each chemical substance that is formed in the atmosphere will be under also temperature of the environment, but will be under partial pressure. And superscript E means exergetic reference environment. So we're not discussing about real environment, we're discussing about model of the environment to calculate chemical exergy. So I repeat, each substance will be under partial pressure. And now we would like to calculate chemical exergy, for example, of the substance that is given in red color, but we know that this substance, this gas, exists in the model of a thermodynamic environment for chemical exergy. In this case, we will discuss so-called concentration exergy, because the concentration of this substance in an environment is described using the molar concentration. The letter X now is used to describe molar concentration of substances within the mixture. And mu0, it is chemical potential of the entire environment. It is thermodynamic environment that will describe for us the atmosphere. And let's say red working fluids, without mention the exact working fluids, under restricted thermodynamic environment, when we calculated physical exergy, can be described using the chemical potential of this working fluid, but temperature and pressure of the environment. And to calculate chemical exergy, now we need to change the environment to chemical potential from the pure substance to the substance within the environment. And the work that will be produced during this expansion process, it is will be the chemical exergy, or if we will discuss more detail, it is concentration part of the chemical exergy. Reaction part does not exist for this example. And to understand how work can be produced, it is work that can be produced within isothermal expansion process from the environmental pressure to the partial pressure of the same substance within the environment. I think this is very easy to understand what means work within isothermal expansion process. We have equation for the work of the isothermal expansion process. Let us assume that we have hypothetical expansion machine, and the work produced within this hypothetical expansion machine, that will be the chemical exergy of this substance L, for example, from the reference conditions to the reference conditions of the exergy reference environment in order to calculate chemical exergy. This equation is well known for us because it's for the ideal gas model for isothermal expansion process. Now, what to do if we have already mixture of gases? Any mixture of gases. For example, it can be a mixture of hydrocarbons, or it can be, if we will discuss environmental analysis, for example, that will be CO2 or NOx emissions, SOx emissions emitted to the environment. So if we would like to proceed with exergy analysis, we need to calculate chemical exergy of the mixture of several ideal gases. And we know that ideal gases can mix spontaneously in all proportions. Therefore, we can adjust equation with many chemical substances with corresponding molar concentration. So this is very important that we always will discuss molar concentration for each substance within these gases. And of course, it will be associated only with concentration exergy, because it will be concentration of each substance. Now, how to proceed with liquids and solids? In general, for energy conversion systems, to calculate chemical exergy for solids and liquids, it is not very common. Maybe for liquids, since seawater is involved, maybe people can calculate for water desalination. That can be the case, but for solid substances, definitely we will not use all this analysis. I repeat, for energy conversion systems. But if for someone exactly this analysis is very important to discuss substances dissolved in seawater and also solid substances in the environment, please, this is given only final equations and description, but also within the description of this video will be given the link. You can find the paper where each value is discussed in detail. Now let us proceed with the solution of liquids, or by other word, mixture of liquids. We can use the same equation as we just discussed for mixture of gases and adjust this equation with one variable, which is called activity coefficient. Activity coefficient describes the behavior of liquids compared to the ideal gases. And very common activity coefficients are used to adjust ideal gas model to describe the liquids. In order to apply this equation, we definitely should have molar concentration of each substance within the mixture. But for example, in refrigeration, molar concentration is not very popular. Mainly we discuss about mass concentration. For example, it is mixtures of artificial working fluid or mixtures used for absorption refrigeration machines. But the same we can say that applied for organic Rankine cycle working with with mixtures of working fluid, and I can give many other examples. So therefore, to avoid problems associated with using of molar concentration and activity coefficients, we can use another alternative method. And in this alternative method, we should assume that mixture that will be formed, it will be homogeneous mixture, two liquids, and will be under temperature and pressure of the environment, and then exergy of mixture will be the mass concentration of the corresponding working fluids. Standard chemical exergy calculated for these working fluids, we already discussed it in the first part of chemical exergy, that we can use these values from the table, and a work of reversible mixing process, because work of mixing process for gases is zero, because gases can be mixed in any concentrations and any compositions, but for liquids we have quite a lot of limitations to form homogeneous mixture. And work of reversible mixing process, it is should be, in order to calculate this value, should be involved enthalpy of mixture and enthalpy of pure substances formed the mixture with corresponding mass concentration, and the same applied to entropy. And in this way, we can calculate chemical exergy of mixture of the liquids. Not necessarily that it will be two substances, it can be, of course, more substances, but equation will be the same. So next step in our discussions, how to calculate chemical exergy of so-called non-reference substances. So let's assume that we are discussing metallurgical process or materials for the energy conversion system, maybe very complex chemical substances, for example, use it as catalyst, and we would like to calculate chemical exergy, but we know exactly that these substances not included within the reference substances that were used to develop, to calculate the standard chemical exergy. Then we need to proceed with so-called reaction part of the chemical exergy. And how to proceed with reaction part, we will illustrate with the help of fossil fuels, because chemical exergy for fossil fuels, it is also not standard chemical exergy. We need to calculate this value ourselves. So let us assume that we have hydrocarbon as a fuel, and we would like to calculate chemical exergy. In order to calculate chemical exergy of any fossil fuels, not only so gas, as saturated hydrocarbon as a gas, we need to write a chemical equation for the combustion process. For all these purposes, as oxidizer always will be used pure oxygen, and combustion gases, it is a mixture of carbon dioxide and water. For the model of to calculate chemical exergy, we need to create the model of reversible isothermal and isobaric reaction process, oxidation process with fossil fuels. We have system boundary with temperature and pressure of the environment, because chemical exergy is already should be calculated at temperature, pressure of the environment. We need to assume, this is our assumptions only for chemical analysis, that combustion gases, so substances formed combustion gases, will be unmixed at the end of the combustion process. In real life, of course, it is mixture of working fluid, but only to calculate chemical exergy, we will assume that these substances unmixed. Then we assume that fuel is coming under temperature and pressure of the environment as a pure substance, oxygen under temperature and pressure of the environment as a pure substance, and the same applied for CO2, temperature and pressure of the environment, pure substance, and water, temperature and pressure of the environment as a pure substance. Then, according to the properties of working fluids, hydrocarbon, saturated hydrocarbon, fuel, oxygen, and CO2 will be in gas phase, but water under temperature and pressure of the environment definitely will be the liquid. And this we need always to keep in mind, that under these assumptions to calculate chemical exergy, water will be in liquid phase. For this chemical reaction that we just discussed, we will write exergy balance. We did not study exergy balances yet, but since this reactor is isobaric, isothermal, and reversible, then exergy in is equal exergy out. Therefore, we will write that exergy of fuel, exergy of oxidizer, minus exergy of CO2, carbon dioxide, and minus exergy in liquid form. As you can see, everywhere will be mentioned standard exergy according to the exergy model that was selected for analysis. And the work, it is maximum work developed per mole of fuel, in taking into account that will be no irreversibilities within this reactor, and heat transfer from the environment under temperature and pressure of the environment. Of course, from exergetic point of view, it is zero. So we can write one more time exergy balance for the ideal reaction process, and from this equation we can calculate chemical exergy of fuel. So using such a model, we can calculate exergy, chemical exergy of any of fuels. So now we need to proceed to calculate the value of work. CV means control volume, so it is open system. As usual, work for the isothermal expansion process, we can write using very well known equation, thermodynamic equation, and we always should keep in mind that all these values, enthalpy and entropy, we will calculate under conditions temperature and pressure of the environment. And I repeat that for temperature and pressure of the environment, water will be in liquid phase. And we know from the already from the discussions about combustion process that this term, enthalpy of reaction calculated in temperature and pressure of the environment, has a special term. It's called standard heating value. So this is characteristic of fuel. The higher this value, the better quality of the fuel if we discuss only energy analysis. But now we're with exergy analysis. And standard heating value can be lower heating value, can be higher heating value, depends in which status, in which state is water. If water is in liquid form, then it will be higher heating value. Therefore, this equation we can already rewrite using the higher heating value of the fuel. But higher heating value of the fuel, this information is already available, or we can calculate also ourselves. And if we will evaluate all these terms, we can find out that chemical exergy of the fuel mainly, the main contributor, it is higher heating value. So mainly chemical exergy depends on higher heating value. And if scientists are not familiar with the equation, or they have no software, or they would like to simplify application of exergy analysis, there are very many publications where chemical exergy associated only with higher heating value, and all other terms are neglected. There are even some recommendations, ratio between higher heating value and chemical exergy of fuels. As you can see, we're somewhere around 1, but for example, for hydrogen and methane, particularly for methane, it is the most popular fuel to discuss, and now more and more we're discussing about hydrogen and chemical exergy for hydrogen. These values already out of the recommended, of the limit of these recommendations. So therefore, better always to calculate chemical exergy of fuel using so proper calculations, this combustion process, but not abbreviate only with value of higher heating value. And I will continue with fossil fuels, because very often we need to calculate standard molar chemical exergy for coal, peat, and oil. And also here we can include biomass, because biomass belongs to the same category of fuel. What is the which complications we can find when we need to calculate chemical exergy of coal, biomass, speed, and oil. The fact that this kind of fuels will have moisture, so water is included, and also there are chemical substances that potentially will form the ash after the combustion process. Therefore, in order to calculate chemical exergy for such fuels, we need to introduce the concept of dry and ash-free fuel. So when we will write chemical balance and also exergy balance for the reversible reactor, we need to exclude water as the part of the fossil fuels, and also substances that after the combustion process will form the ash. So it means that fuel that we will consider to calculate chemical exergy already will be not exactly this fuel that will be used for real combustion process, because humidity, water, and potential ash forming substances will not be included. Everything other will be the same. All substances will be in unmixed form, and we can calculate standard chemical exergy for each of these pure substance under conditions that we discussed before. Yeah, and also if we would like to abbreviate chemical exergy only with higher heating value, also higher heating value should be calculated not for real fuel, but for fuel under assumption that it is dry and ash-free fuel. And let us proceed further with this equation. The problem is that in chemical thermodynamics and chemical engineers, they are not working with higher heating value, and they prefer not to work with entropy. It is not variables for the chemical analysis. Therefore, this equation where enthalpies and entropies are included, we can replace with Gibbs function. And Gibbs function, it is very popular in chemical engineering. Therefore, for all chemical engineers, very easy to describe the concept of chemical exergy because it is associated with Gibbs function. And equation immediately will be much simpler because only Gibbs function will be included, and also standard chemical exergy of all substances that included in the reaction for the fossil fuels or substances that does not exist in the reference environment. And the negative value of Gibbs function means that it is spontaneous process. It is the second law of thermodynamics. And we can conclude that for all substances, non-reference substances that we cannot find in the reference environment, thermodynamic environment, we need to consider reaction part of chemical exergy, and always we need to calculate the value of chemical exergy using Gibbs function. So without Gibbs function, we cannot calculate this values. But Gibbs functions, it is also variable from the second law of thermodynamics that easy to find for all working fluids. And next, our lecture will be already dedicated to exergy analysis. So we covered concept of exergy, we discussed kinetic potential exergy, we discussed physical exergy, we discussed chemical exergy, and now we are fully prepared to continue with exergy analysis. If you like this video, this information is useful for you, please give a like to our work. Please subscribe our channel and share the link of this video with your colleagues. Thank you.